definitions. I want to go through some definitions that we'll use throughout our course. We all, first of all, want to make sure we're clear with the terminology or the notation. A prime, a bar, a tilde all mean not x, or x inverse. This means x and y, x or y. Right? So the first definition is that of a literal. Right? What is a literal? A literal is an instance of a single variable or its complement. Okay, so essentially it's an input variable. All right, it's either essentially a wire. This is then x prime. It's either wire or the output of an inverter. That's a literal. Okay, so a signal or its complement is a literal. So x is a literal, x prime, x bar is a literal, y is. Signals can have very descriptive names. They don't have to have just letter names. You could say an alarm, which is true or false if the alarm is on or off. You can have anything you want. Okay, as long as it's an inverse or a single bit. What's not literals is when you start to combining them and doing operations on them. So x or y, right, is not an individual bit or its inverse. It's an or function. This is an and function. It's not. All right. The parts, right? So x and y themselves are literals, but the whole thing is not a literal. Okay. All right. Fine. We need to give you some more terminology. Product term. What's a product term? A product term is the anding of, let me just cross this out, one or more literals. Okay. One or more literals. All right. So I have here x prime and y prime and z. What's going on here? Well, x prime is a literal, y prime is a literal, z is a literal. They're all anding together. That's a product term. Okay. Literal, 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 anded together. That's a product term. As many as you want. And in fact, here's the kind of the one special case. An individual literal by itself gets to be called a product term. All right. So an individual literal is a product term. And we'll see kind of where that comes into play again later. All right. What's not product terms is when you do any kind of or operation in a term. So this term cannot be a product term because you're doing an or. Similarly, you do not have a product term when you have the inverse or the prime, the not of a whole sub-expression. Okay. That does not count as a product term. All right. So you can only have individual inputs being inverted. All right. You cannot have an overall, collection, right? This says take the quantity x and y and invert that. Okay? So we'll hold off on those. Those are not product terms. The key thing about a product term to recognize, again, because it's an and function, it only outputs one for a single combination, just like we saw here with these checkers, right? And functions output one for a single combination. Okay, so I'm going to give you definitions little by little as we go, and we'll build on them throughout the lectures. Well, now let's add the idea of sum term. We just did these OR gate checkers, all right? That's essentially what a sum term is. It's an OR gate of two or more literals, okay? Or again, a single literal by itself counts as a sum term. So here I have the sum of z bar, which is a literal, w is a literal, y is a literal, that's a sum term, right? X bar by itself is a single literal, so it counts as a sum term. What's not a sum term is a and b or c, right? So again, just borrowing from normal arithmetic notation, if we don't show the product, it's implied, right? Two variables just written next to each other implies the product of those, all right? And so that and means that it's no longer a sum term. We can only do an or operation. Similarly, this is not a sum term because you have the whole quantity be inverted. A sum term has to have only individual literals being inverted. The key identifier about this is a sum term only evaluates to 0 for a single input combination. So going over here, all right, x or y bar, you need to plug in 0 and 1 for x and y to get a 0 coming out, and only that combination will produce a 0 coming out. All right. And so product terms and sum terms will be used as we go, all right, to help us check for certain combinations. Okay, two different ways of checking for combinations. You can either use an AND gate and produce a 1, or an OR gate and produce a 0. So just to check yourself, I would encourage you to take a moment, pause the video, and go through and say, are these valid sum terms? Are these valid product terms? Are they both, or are they neither? All right, well, let's look through some of this. Here, we see that this quantity, y and z, is being inverted. Right? Essentially, we have w and x, but then we have y and z, whose output is being inverted, and then we AND them together. Right? Well, this is not a valid product term. A valid product term has to only have inverts or complements of the inputs, essentially of the literals. All right? We can't invert a whole sub-expression or a quantity. So this ends up being neither. It's definitely not a sum term because it's not ORs, right? Let's go on. Well, is this a product term? And the answer is yes. Even though you see the parentheses, you're not doing any operation on that quantity, right? And in fact, just like from normal arithmetic, the multiplication operator is commutative or associative. It doesn't matter what order you do it in, all right? You can do x and y and z, or you can do x and y and z. They're both the same, right? Borrowing from normal math or normal arithmetic. The same applies for our logic. So these parentheses really are superfluous. We don't need them. Thus, we get down to w into x and y and z, and that's exactly a product term. Literals being ANDed together. W or x and y or z. Is this a sum term? No, because it has a product going on. It has an AND that's being performed. So this would be neither. W or y is a sum term. It's two literals being ORed together. This term, w or y or z, looks like a sum term, but again, we're taking the inverse of the whole output or the entire quantity. That again precludes it from being a sum term. So right now I would say it's neither, though what you'll learn as we go through, in a week or so, or learn in the next lecture, is that with a little manipulation, this can become a product term. For now, though, you don't have to worry about that. By looking at it, you would say it's neither. Lastly, w, all by itself. A single literal, all by itself, gets to be counted as both. All right? So you should start to recognize sum terms and product terms, all right, and which ones are valid, which ones aren't. All right. So here you can see, again, our answers.